So in this lecture, I'm going to cover springs, and then we're going to define power, springs and power. Okay, the big thing I have to explain is the spring constant of a spring. So you look here at this equation. This equation, referred to as Hooke's law, it's the equation for calculating the force of a spring. And the only time a spring is going to give you a force is if the spring has been compressed from what we call the equilibrium position or stretched from the equilibrium position. Okay, so what is K? So K, first off, is referred to as the spring constant, and it's in units of Newton per meter. So let's do an example. Best way to understand it is with an example. So see this spring here in this diagram? Let's say that this spring has a spring constant of 100 newtons per meter. So what that's telling us, Newton per meter is 100 newtons per meter is telling us if we grab this spring. Oh, and by the way, see right here, what's the force of the spring right now? 0. And there should be a unit on there, 0 newtons. And this should be 0 meters. The spring is not being stretched. The spring is not being compressed. If you grab this spring and pull it, let's say 1 meter. We pull the spring out 1 meter. First off, which way will the force of the spring be? If you pull a spring to the right, the force of the spring is going to be what? To the left. Can you wrap your brain around that? You pull a spring to the right, the force will be to the left. And by the way, see this negative in the equation? Force of spring equals negative kx right here. What this negative is saying is that the force of the spring and the displacement of the spring will always be opposite. If you pull a spring to the right, the force of the spring will be to the left. If you push a spring to the left and compress it, the force will be to the right. Every year, kids find this negative to be highly confusing. My recommendation to you is to ignore the negative. It's confusing. Ignore it, because remember, at the end of the day, what does plus and minus tell us in physics? Direction. So figure out which way the force of the spring is, and then, that'll either be plus or minus depending upon how you set up your sign convention. So see here, what we're saying in this diagram here, we're saying to the right is plus, to the left is minus. So our delta x is positive 1, and then the force of the spring is going to be what? Negative 100. You guys see that? If the spring constant is 100 newtons per meter, and we pull the spring 1 meter, what's the force of the spring? 100. Okay, let's say instead of 1 meter, what if I pulled the spring 0.5 meters? What would the force of the spring become now? 50, right? All you're doing is you're plugging in here. You're going force of spring, negative, so the spring constant is 100 newtons per meter. For 0.5 meters, the meters cancel. You get negative 50 newtons. The negative simply means to the left. Got it? Okay, so spring constant is Newton per meter. Now, next thing I want to draw your attention to, if you graph force of spring versus the stretch of spring, you're going to get a straight line, okay? So look, what happens to the force as you stretch a spring more, what happens to the force? The force goes up, 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 and you get this linear graph here. Now the thing that I've been pointing out to you is that you can take physics equations and have them fit the equation of a line. So the equation of a straight line is y equals mx plus b. The y-intercept's going to be 0. Now why is the y-intercept going to be 0? Well look, if the stretch of spring is 0, what's the force of the spring? 0, so you have no y-intercept. Now if you take force of spring and put it on the y, so see right here, force of spring goes on the y, Okay, the stretch of the spring, the delta x, that's how far the spring is stretched. That goes on the x-axis, right? So what should the slope be? The slope of this graph is going to be what? The spring constant. So you're taking Hooke's law and making it fit the equation of a straight line. That make sense? Okay, final thing, you need to be able to calculate the energy stored in a spring. So here is the energy, that's the equation for energy stored in a spring, 1/2 kx squared. You now know what k is. It's the spring constant. And then what's x going to be in that equation? How far the spring is either stretched or compressed. Okay, 1/2 kx squared. This is for force of spring. This is for energy of spring. Got it? Okay, final thing for today is power. So look, power. We're changing gears now. Power. Oh, so my two pictures. People, when you say power, a lot of times people think of cars, you know? Like, what am I looking to get right now? A power wagon to pull my trailer. Okay? Or people think of light bulbs when you talk about power. Like, oh, the power is out. The lights don't work. Now look, there's two definitions of power. It just depends upon what type of problem you're doing. Sometimes you'll be doing a problem where it's talking about like a guy is doing work and it takes him 5 seconds to do the work, calculate his power. If the problem is using work, then you're going to use this definition of power. Other problems are going to be talking about energy. Your refrigerator uses this much energy in this much time. So you could calculate power looking at it that way. But look, either way, you're going to get the same unit. Because what do we measure work in? Work is measured in joules. Time is measured in seconds. A joule per second, anybody know what that is? That's a watt. That's a watt. A joule per second is what we call a watt. Now, what if you're looking at power this way? Well, you're going to get the same thing, because what's energy measured in? Joules. And what's time measured in? Seconds. So you get the exact same thing. It just depends upon how the problem's written. Work and energy are very closely related. Now, final thing I want to show you. What's the work equation? The basic equation for work. Force times displacement, right? Oh, and remember, when you're using that basic work equation, the force and the displacement have to be parallel to each other. Remember that from Tuesday? All right, now, at this point, anybody notice anything? What is displacement over time? Velocity. So this becomes a third equation for power. You could say that power is equal to force times velocity. The force doing the work multiplied by the velocity of the object. Okay.